So, no matter where you are in the homework officially, stop doing it and go to 4.9 just immediately. There's always going to be a couple of questions in every section of homework that's a little tricky. It just is, right? There's conceptual going, but most of it is just, if you know derivatives, you have to know antiderivatives. It's just thinking backwards, which is not easy, which is why all of algebra is more difficult than whatever came before, because algebra is thinking backwards. I don't know if there's going to be any questions, if anybody's jumped in the homework and got anything weird yet, but if not, no worries. Get in there, do it, see what's happening. In general, your primary focus is new homework, and you do old homework as you can, as you get time. So, last time we finished up 4.9, I took little baby steps into 5.1. Let's see. Something's happened. Okay. Let's see. 2, 4, 6, 8, 10, 12, 14, 16, 17. All right. All that matters is you're here. That's all I care. All right. Here we go. 5.1 is the beginning of, like I told you, there's two big ideas in calculus that we learn. We learn derivatives, and then we learn antiderivatives. 4.9 is just the tip of the iceberg with antiderivatives. There's a lot more to them. And I think I tried to warn you, we're about to do something. We're about to get into something today that's going to feel very disconnected. And then we're going to connect it. And then everything's going to be so beautiful. Because I will warn you right now, 5253 are not limit definition of derivative, but they're equivalent to it in a way. It's the full process you have to go through. And then we're going to make shortcuts. I think I said something about this before. Do you guys remember the limit definition of derivative? You guys remember limit f of x plus h minus f of x over h, limit as h goes to 0. Remember that stuff? And that was how we got the derivative. And then chapter 3 came along and said, what the hell are you people doing? And we made shortcuts, yes? Product rule, quotient rule, we went next to the end. Hold up, you guys with me? And then we said, get out of here. Every now and again, limit definition came back to go, and we proved something for you. And they were like, thanks, man. And we said, no. Right? Essentially, the same thing's going to happen. We're going to talk about the idea of something that seems disconnected, and then we're going to connect it and make shortcuts. Anything else? Okay. So here's the key idea that 5.1 starts to delve into. Oh yeah, you want to do that? No. Okay. If I have a function, let's say it goes from A to B. So I've got my little function. Look at that little function. It might exist beyond A and B, but all we care about is between A and B. Yes? Now we're going to extend this later. It actually does not need to be continuous, believe it or not, for this next bit. But we'll start with one that's just kind of looks a little bit more normal. So I will say the area below the curve. When I say that, I mean from the ground to the, from the curve to the ground. And the ground is the x-axis. You guys with me? The book will say it sometimes, the area under the curve. Technically, there's infinite area under the curve because it goes down for it until we stop at the ground. You guys with me? I really want that to make sense. So we want to find this area. Is that shape one that we know the area formula for? Hell, I didn't even tell you what f of x is, right? If f of x was constant, then it would just be a rectangle. And we're like, yay! If x is not constant, I don't know what this shit, right? So we go. And just to remind you, I mean, if I had to find the area of this shape here, we don't have an area formula for this shape, do we? This could be like a crayon nub. There is no crayon nub formula that I know of. But couldn't I just find the area of the square and the area of the triangle and add them together? Okay. So if I can break down the area I've got into shapes that I know the area formula for, then I can find the area. Obviously, I can't break, this is easy to break down because it's got nice straight lines. Straight lines have a good chance to make a shape that I know the area formula for. Is everybody semi with me? The minute I've got curves that aren't circular, because I know the area formula for a circle, this ain't circular, shit. Say again?
It makes things awkward.
Make things awkward?
Yes.
Oh, okay. Thankfully I did. Well, sometimes I do. So from A to B, I want to find that area. What I'm going to do is I'm going to estimate it. I'm going to use something not perfect. I'm going to get an estimate. So what we're going to do is we're going to use rectangular strips. So just to kind of throw this down there. So if I break this interval up into several sub-intervals, let's say. So I'm going to break that interval up into 4 sub-intervals. Right, don't freak out about the word sub-interval. Just little pieces of the interval. Is everybody with me so far? Not much has happened. Okay. This would act as the base of each rectangle. The next thing I have to consider, and let me just draw this just so you can see. What if I used, how tall would each slope? Well, let me just ask you this. I'm about to draw in rectangles that will approximate the area if I add up all their areas. Why will it be an approximation? Because the top of my rectangle is going to be flat, and my function is not flat. Okay. How tall will the rectangles be? How tall, what should determine? Why won't my first rectangle go up to here? Why would that make no sense?
Because you're under the curve, so.
Yeah, why wouldn't it go up to here?
Because you want to go up.
So what should determine the height of each rectangle?
The max.
The actual function.
The function value. All right, you guys with me? That kind of makes sense intuitively, yes? It's like, why the shit would you go past there and you want to go up to the function? But since the top of my rectangle is going to be flat, what specifically determines how tall the rectangle is? Let's start with that. So to be really, really honest, I could use any output in this interval to determine the height of my rectangle. Because any of it's going to be an estimation anyway. You guys with me? I'm just estimating the damn thing. So I just need something that's showing me where the function is. Okay. What we generally break it down into is 3 options. We have, I could use the left endpoint. So what would that look like? So if I use the left endpoint, the height, so is everybody with me that this is the base of my first rectangle? Right here is the base of my first rectangle. We're currently just trying to figure out how tall to make the damn rectangle. Yes? Okay, so this is the base of the second one, the base of the third one, blah, blah, blah. Okay. I have options. And what we normally do, like I said, instead of using infinite possibilities, we just go left, right, or midpoint. So if I do left endpoint, my rectangle is going to be as tall as the output at the left side. So I'd go like that. That would be my first rectangle. I could have used the right. So is that going to be an under or over estimate?
Under.
Under. I could have used the right endpoint. Yes? Then that would have been an overestimate, correct? But you see how either one's fine, because what are we doing? We're just getting an estimate. Okay, let me stop for a minute. Is everybody with me? I really want the parts of this to make sense, because at the end of this, it's find areas of rectangles and add them. In the middle of this funky ass calculus course, we're gonna be taking areas of rectangles and adding them. You're like, okay, this is nice. It's not gonna happen for a long time though, so enjoy it while you can. Does everybody see the choices that went into this? Now, how many rectangles did I choose to use in my current example?
4.
4. I could have used 8. I could have used 2. I could have used one giant frickin' rectangle. More than likely, that would have been a really bad estimate. So obviously, how could I improve my estimate? Use more rectangles. How can I make my estimate not an estimate, but perfect? Infinite rectangles. That sounds like it's going to use the idea of limits. Yes, limits are coming back. They never go away. All right. What I call them zombies. Last time they were zombies. So if I kind of continue this little trend, I'm going to use the left endpoint for the height of the second. You guys see how I did that? Do you guys see how I did that? Right? If I'm using left endpoints, if I'm on this second second rectangle, I go up and oh, that's how tall it is. Yes? And then the third rectangle is going to be right there. The output at its left side, that's how tall it is. And the last rectangle is going to be this tall. Okay. And then I have to have more information, obviously, but if I gave you what the function was, could you not figure out what the areas were? There's one little thing though. Let me stop for a minute. Is everybody really with what we've done so far? Okay. I really want you to let this be not too tricky. It feels like I haven't given us much information. And you know why? Because I haven't. But I have given you enough information to tell me how wide each rectangle is. Not a number, but an expression. Believe it or not. So, listen. Go with me for a second. I want to make sure you guys get how this is physical. Does everybody see this wall over here? I don't know if you noticed we have a wall here. Everybody agree with me? Maybe that's about, 20 feet, let's say. Just go with me. I don't know if it's 20 feet. I haven't measured. You guys with me? Let's say Jeff freaking goes full weirdo, and I just bring in these, I want to bring in wood slats, and I just want to put wood slats all down this. You with me? Okay. Bear with me. I want to go retro in there. It's 20 feet long, and let's say, math boy here, has to use 5 slats. 5, is everybody with me? All with me what the word slat is. It's just a rectangular strip of wood. Yes? How wide will each one have to be? So let me review what we know. 20 feet of distance, and I want to use 5 pieces of wood.
4.
Yes? How wide would each one have to be? 4 feet. Does it make sense? How'd you get that? You just took how far you had to go, divided by
5.
5, which is how many I want to use, yes? And aren't they all rectangular? Yes? You see how that's exactly what's going on here? How far do we want to go? How far do we want to go? Say again? No. I want to know exactly how far we have to go. I'll say from A to B. So, if I had to go from 7 to 16, how far do I have to go?
No.
Okay, so I have to go from A to B. How far do I have to go? How'd you get 9?
B to A.
Subtracted it. Yes, go ahead.
B minus A.
B minus A. Kick ass. Whatever the should be is, whatever should A is, how far apart are they? B minus A. So everybody with? As long as B is the big dude, so we always assume B is bigger. B bigger. Okay. And how many rectangles am I using in this case?
4.
So it will be B minus A divided by 4. Yes? So this is 7 and this is 11. It'd be 11 minus 7 is 4 divided by 4. They would each be 1 wide. How do I figure out how tall they are? Well, I have to be given the function, and then I just plug shit in and figure out how tall it is. How tall it is based on the function output at the point I decided to use. Is the physical nature of this problem making sense? Okay. And it does feel disconnected from everything else we've ever done in this class. You guys, I want you to know I'm aware of this. So we take this really weird side trip, and then we bring it back and go, oh, look, it's the same as this shit. And we go, holy shit. And then we get a shortcut one. Thank you, guys. Okay. Oh. In general, remind me, how do I make, oh, got it. Well, first off, let me tell you this. The symbol we use for width, x-axis. If I start at A and I go here, what changed? What changed? Yes, say it again.
1x.
X changed. You with me? If I move along the x-axis, X changes. Oh, that's amazing, Jeff. Thanks for that. So we give the symbol for the width, we call it delta x, because that's how much x changes as I step around, yes? So we call the width delta x, change in x. And what did I say earlier? How would we improve? Y'all agree that if I add up all the areas, I'm not going to get the right answer? It looks like that was an underestimate. That's over. That's under. That's a little over. So it looks like it's going to be close, maybe? Maybe a little under. Yeah. How would I improve that again? Use more rectangles, right? I call it cranking up the resolution. It's sort of like the difference between playing the first Mario game and then playing whatever the shit's out now. Alright. Okay. So then underneath here will be N for the number of rectangles. Because again, math people, very creative. Number of, she said. Okay. So if I was using 6 rectangles, I would have divided by 6. That'll tell me how wide each rectangle has to be. Okay. So dear God, Jeff, can we do a concrete example? Yes. Let me give you this. Oops, stay there. Yeah, I'll do it that way. Yeah, that makes sense. So many people, this is not a good name, so. Good try. Oh, sorry. You don't have to do it twice, John. So let's do this first side together. John, I started my camera, did I?
Yeah, it's recording.
Thank God. Let's say we want to get the area between the x-axis and this function here. Everybody together. We want to know. From x equals 0 to x equals 4, let's say we want to use 5 rectangles for some reason. Yes? How wide would each rectangle have to be? Well, how far do we have to go?
0.
4 minus 0.
4 minus 0?
5.
5.
5, so it's 4/5. Make that into a decimal. 0.8, good. 4/5 is 8/10, which is 8/10. Okay, is that cool? Find out the width, coolest little thing in the world. Makes physical sense. Think about weird ass Jeff in his woods, slats going up on there. Now, everybody's favorite thing in the world to do, sketch the function. don't go crazy. I know what inputs I want to use, yes. I can use any inputs between zero. Let's use 0, that makes sense. We have to know how to sketch the function. So when I plug a 0 in, what do I get? 6. When I plug a 1 in, what do I get? Yeah, 6 divided by 2, 3. When I plug a 2 in, 6 divided by 3, which is 2. And when I plug a 3 in, 6 over 4, which is 3/2, which is 1.5. And then 6 over 5, which is 1.2. Okay, so it really kind of flattens out there at the end. So it doesn't have to be perfect. So we want the area under this curve. Well, and again, when I say under the curve, I mean to the ground, to the x-axis. And then the width. So here's what I mean by that last part. I want to set up like I did earlier where the base of my rectangles are going to be. Okay. And we said the width is 0.8. So I start at 0. So the first rectangle is going to go from 0 to 0.8. And then from 0.8 to 1.6. And then from 1.6 to 2.4. Good. And then from 2.4 to 3.2. And then from 3.2 to 4. Okay. So a little busy down there, but we'll be okay. Stop for a minute. The picture doesn't have to be perfect. It's just a visual anchor. Kind of remind yourself what's physically going on. Is everybody with me so far? What we've done? Okay. So your width is going to be sometimes nice, sometimes gross. Oh well. Now let's draw the rectangles in. We're going to use, at first we're going to use left endpoints. So my first rectangle lives here. So I'm going to go left end of that. What's the output there? So that's how tall my rectangle is. Yes? So that is quite a bit of an overshoot. And it makes sense, this whole thing's going to be an overshoot when I use left because my function is always going down, yes? So if I use the left endpoint, I'm always going to be over it. Yeah, I am over it, be quiet. So then the next one, and then I just keep going. So my next rectangle lives between these two, so it's going to be right there, right? This is my left endpoint for my next rectangle, so it's going to be right there and over. And then it's going to be right there and over. And then it's going to be the output for 2.4 and over, and then the output for 3.2 and over. So at the end there, it got a little flat. Much like our beautiful flat Earth. They're out there, kids. Somebody with me so far on the picture? You could do this problem without the picture. You could, but that would be really slow. You want a visual anchor for what the hell you're doing. So we have established rectangles. I know how wide each one is, but how tall is each one? How tall is that first one? We'll call this rectangle 1, 2, 3, 4, 5. It's amazing, John. So the height of the first one, yeah, is going to be f of 0, which is 6. What's the height of the second one? Jeff. Oh, I'm doing fine. Jeff will be fine. What's the height of the second one?
3.
Yeah, when you plug a 1 in, 6 divided by 2 is 3. What's the height? Oh, I'm being silly. Yeah, there's 0 and 1. Let me start over. Just so you know, I initially was going to use 4 rectangles. And then I decided, no, I got to make it gross so we can do it together to show you how things get gross. What should be my next input? 0.8. Yes, thank you. So many guys are like, should I say something? This poor guy is off his rocker. Now somebody's got to help me out. What is 6 divided by 1.8. That's 60 over 18, which is 10 over 3, which is 3 and 1/3. 3.33. Is that right? Okay. 3.33333. Okay. So ready with what's happening? Are you guys with what's happening? Okay. The height of the third rectangle will be f of 1.6. The height of the fourth will be f of 2.4. The height of the fifth will be f of 3.2. All right, now, are you guys interested in a bit of a shortcut? Really? So let me show you something. If you don't know about this already, I'm sorry. Oh, shit and a half. What have I done? I have changed things. I destroyed everything. There we go. Oh shit, it was back for a second. So if you got your calculator, grab it. I want to show you some kind of nifty that's going to help on these. Maybe. Let's see what happens. There we go. Focus. Focus. Zoom. Zoom. Okay, so everybody put the function in. Be really, really careful. You gotta tell the poor little calculator what the bottom is. Don't have no eyeballs. It don't have no ears, so it doesn't have to listen to my horrible grammar. You guys know about the table function, right? You guys know about the table thing? I don't know if you know this about the table. Table set. If you hit second window, you go to table set. And the most powerful thing to have this set to is ask for independent. So everybody with where I am. Go to second window. It'll take you to table setup. Change that to, I don't give a shit what these are. Change that to ask. Is everybody with me that wants to be with me? Go to table. And now I'm going to delete the shit that's in here. Go away. I don't care about you going. So get it all nice and empty. And now you can just tell it exactly what you want. I want 0. I want 0.8, 1.6, 2.4, 3.2. Does that seem useful? Yeah. And it's not it's not the end of the world that we're going to kind of round in the middle, because the whole thing's an estimate anyway. So it's not a horrendous thing. So now I know all these heights. 2.308 will say, 2.4 is 1.7647, and 3.2 is 1.4286. Okay. There's all my heights. Yes? So how do I get the area of the first rectangle? Yeah, it's going to be how wide it is. Everything is 0.8 wide, right? So it'll be 0.8 times, there it is, 6. Is everybody with me? Got the height of the first rectangle, and I got the width of every rectangle is 0.8. And of course, what's 0.8 times 6? 4.8. I'm going to develop a shortcut here in a minute. What's the area of the second rectangle? 0.8 times 3.3333. Just put a few 3's in there. Which is just about 10.3. I don't know. Am I doing it right? No, it's not. It can't be 10.3. It's what did I do? Oh, I forgot the point. So it's 1 point. 2 point something?
6664.
Yeah, I'm trying to do something weird in my head. It's not working. 2.6664.
6664.
Okay. So it's probably 26666. Okay. So just do that.
Oh my.
Do you guys notice that? Let me see if you guys are ready. Well, is everybody with me? What's happening so far? right?
Multiply.
Well, we would keep going and we get the area for every rectangle, then we add them all up. But can we do something that actually recognizes that every single one of these stupid areas has 0.8? I'm gonna do area 1 plus area 2 plus area 3, blah, 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 area 5. 0.8 times the height, plus 0.8 times the next height, plus 0.8, so can't I factor a 0.8 out? So wouldn't this just be, wouldn't the total area just be 0.8 times, add up all this shit, yes? 0.8 times 6 is the first area. 0.8 times 3.333 is the second area, yes? So what you can do is you can add up all these.
Oh, yeah, I know. Right, like 0.8 times
14.
the sum of.
Yeah, just add up all the heights and then multiply what you get by 0.8, because then it would be distributed. You get all the areas that you need. That's the first little shortcut for us there. All right, go for it. Just add those up and then multiply by 0.8. Let's see. Yeah. All right, I got a number. And by the way, trust me on this. 1, 2, 3, 4, 5, thank the gods, right? Learn from young Jeff. I remember when I first learned this, I always added one too many things. Like, did I use f of 4? Did we plug 4 in to get a height? Why wouldn't we? Because 4 is the right side, yes? But you see how it's really easy to get into the rhythm and you just plug everything in? And then you got one too many rectangles. So just every now and again, make sure you're working with 5 rectangles, yes? If you're not, go, wait a minute, did I lose somebody? Did I create somebody? Okay, is that, you guys with me? That's a really easy check, just to make sure everything's right. You're not throwing too much stuff in there. Anybody get that yet?
11.83.
What'd you get?
11.83.
11.83? Oh, I see what it is, yeah. Yeah, it should be like 11 point something. What did I do? Oh yeah, there we go. 11.8, I got 11.86, but I might have plugged something.
I might have cut it. I didn't round that 2.308.
I got 11.868.
Okay, so we all got about 11.867
Something.
roughly, or 8, yes. Yes? Can you guys tell me, is that too big or too small from what it should be? Too big. Because every one of those rectangles, especially the first one, overshot. Okay. So one thing we could do is we could balance things out by doing the right endpoint. If I use the right endpoint, every rectangle will be not tall enough. It will undershoot. So then I get a range for what it will be. All right, so let's try this again. Here we go. I'm gonna graph it again. We'll do it we'll do quick mode here. So I got my 0.8. I got my 1.6, 2.4, 3.2, 4.0. Just to cut to the chase. Sorry, there it is. Yes? The picture does not have to be perfect. It just needs to be close enough. You just need a visual anchor of what's going on. Yes? Now when I draw in my rectangles, here's how I do this. If I'm using right endpoint, I go to the right side, I go up. When I hit it, I go over. Right side, I go up. When I hit it, I go over. Yes? If I'm going to use the right endpoint, I go to the right endpoint, I go up, I hit the function, and I go over. Make my little rectangles. And like we said, every single one of those, devil inside. No, every single one of those under estimates. Now here's, do you guys notice something? Does anyone notice something mathematical? We don't have to do much work at all. Most of our work is done. Does anyone see that? What's the one thing I'm missing? I already get all my heights, didn't I? I already know what f of 0.8 is, don't I? So what number in this list am I not going to use? Real quick, is the first rectangle this tall? Yes, the first rectangle is this tall, yes? Before, wasn't the first rectangle that tall? That's where that 6 came from. Am I going to use this? No, I need the next number. I need 4. Now, if you don't see what I'm saying, you can do everything we did earlier all over again. But I've already calculated f of 0.8, f of 1.8, right? We already have those, yes? If I just get f of 4, bam! So now it's going to be, area is going to be my width times 3.333 plus 2.308 plus 1.7647 plus 1.4286 plus 1.2. So I don't use the first height from before, but I do include the last input because now it establishes how tall the last rectangle is. Not much to it. There really isn't. So here, the first rectangle was as tall as the output at 0. Yes? So that's why we use 0. The last rectangle was as tall as the output at 3.2. I didn't use 4.0, did I? I didn't use 4. I didn't need to. Now, I don't give a shit about 0. No rectangle is as tall as f of 0, but there is a rectangle as tall as 4 now. So I have to forget about 6. I don't need him. But I do have to include f of 4, because that's how tall the last rectangle is. So it just kind of does this, it just goes, it just shifts over. Why does it make sense? Because what do? We shift it over. So of course the things we use have to shift over. I don't know if you guys are with me. And again, if none of what I just said makes sense, just redo everything if you want to. I don't know why I'd want to, because it's the same dumb numbers. So now, if I do this, let me see. You're going to try to do this in your head. Why not, Jeff? Now I'm gonna get fudge. I'm not gonna do that in my head. If I knew what that was before, then yes. Let's see. Baby, come to. Here, I'll do it in there. No, Jeff, you screwed up. Oh, because I did 8. Damn it. Alright, we'll just do it all over. There. So now I get this. Anybody else get that? Anybody? I think I plugged it in there right. Bam, bam, bam. Oh, I left one out. Damn it. So it's not that. I left out 1.4286. There we go. So 8.02744. Is that better? Just add all these up and multiply by 0.8, yes?
You didn't multiply that 1.2 by 0.8? Oh, never mind.
Is that what you got? Yes? Okay, thank you. Just add and shit, multiply by 0.8. Shouldn't take that long. So this kind of jives with what we thought. This was an overshoot. We could see it on the picture we drew. This was an undershoot. We could see it. So what's the best way right now to get a really good estimate? Averages, yeah. So if you add those together, divide by 2, you get roughly 10. Let's see.
Oh, I didn't multiply it by 0.8.
1989. So you'll get 9.945, something, let's see. Yeah? It's alright? I mean, I can't do more basic shit, but I can do that in my head. So roughly 9.9, let's see, let's get it exactly right, so 11.867 plus 8.02744. You have to point out, Jeff, divided by 2, 9.947, that's pretty good. So that is our best guess. We got a low estimate, we got a high estimate, so if we average them, that's our best guess. Is everybody kind of with me? Everybody roughly with me? I need you to be like the basic nuts and bolts concept of just estimating using little rectangles. It's almost too nice to believe that that's what we're currently doing. Now, does anyone want to know the exact answer? Me too. Oh yeah. If you have a calculator, the symbol that represents the perfect area, and we're going to catch up to it in a bit. By the way, do you guys see number 6? And by the way, this is second trace to get to calc. See number 6? You can get the derivative at a point, yeah. And then number 7, that's the symbol that means the infinite rectangle area. This little symbol is literally the letter S for sum stretched. That's what that symbol is. So we're going to focus on the symbol a little bit later, but right now I just want you to realize that just means find the area under a function using infinite rectangles. That's what that means. So I'm going to tell it. So if you select this, now make sure you got the function in there, yes? Otherwise the calculator don't know shit. So let me come back. Second calc, number 7, and then it's going to graph it. Ooh, thank you. And then it's going to say x equal what? 0 to x equal 4. Look at that shit. Gaze upon that shit. Come back to me. I mean, what did we get? We got 9947 using 5 rectangles like Fisher-Price time, yes? And the actual answer is 9656. I mean, that's flipping close as shit, yes? You guys with me? Obviously, the freakier the function gets, the more thrown off our estimate that it can be if we use not enough rectangles. You guys with me? You guys kind of with me? I mean, if I have a oscillatory thing and I happen to line up my rectangles so they always hit the time, I mean, they're going to be on over estimate. It's if I have a function that's going crazy very quickly, my rectangles can never quite catch that if I don't use enough. You guys kind of with me? But in every case, how do you make it better? More rectangles. I have a fever, and the prescription is more. I'm sorry, nobody gets that. It's okay. More capital. No, more rectangles. That's all right. Nobody got your numbers. One person got the reference. No. So I want you guys to do the one on the back. I have graciously made a computer draw stuff for you already. So now you just have to draw the rectangles in. Feel free to start to catch up to you a little bit. Is that what you guys got for the first bit? Yeah? Is it going to be under or over? Under, yeah. How many rectangles actually went over? Just one. And all the other three, I mean, this one went under way big time, right? Does everybody really see what I mean when I say under, yes? It's not accounting for that much area, so it's going to underestimate what the total area should be. That's the only one that went over a little bit. And it kind of fills this dude in, and then these three are under. So it's going to be lower than it should be.
The next one will go a little over too.
Oh, then I didn't draw the last one.
Yeah, you
I stopped short. So that one goes over. So that one accounts for this one, and then these two. Yeah. So I do my own rule. 1, 2, 3, 4, 5, 6. Yay! I'll talk about this. I'll talk about this when we're done with this one. I'll put the notation in at the end. But right now, I just want to focus on the physical idea of the problem. So if I just do the width times f of 1 plus f of, why did I put 0.5? 1.5 plus f of 2 plus f of 2.5 plus f of 3 plus f of 3.5. 1, 2, 3, 4, 5, 6 rectangles. Everybody notice I didn't plug a 4 in because that doesn't determine the height of anything. It's a right endpoint for the last dude. Now, if you want to use the shortcut, it's completely fine. So if I put the function in here, where'd it go? There it is. Go to my table, delete, 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 and then I can put in there 1, 1.5, 2, 2, Jeff, 2.5, 3, 3.5. So then I get some nice numbers, 0.5, 1 plus 2.75, 4, 4.75, 4, oops, 5, 4.75. All right. So parts of this are obviously really exciting. Oh, it's better than being completely confusing. So really, are you guys understanding that you should love the shit out of this? Yes? Parts of it are a little boring. That's a beautiful trade-off from not making any damn sense. Now I just gotta add that stuff together, cut it in half, right? What 475 and 475 is 9.5, 14.5, 18.5, 19.5, 22.25, I think. Trying to do this in my head, so 11.25? 22 so 11.125? Yes? Okay. Yay, Jeff, every now and again. Okay, so I'm sorry. Did everybody made it at least that far? Keep going. Try to do the right endpoints now. And of course, we already know that's going to be an overestimate to kind of balance out or under. Hey guys, real quick. If I would have went from 2 to 4 instead of 1 to 4, if I would have went from 2 to 4, can anyone see why it would be silly to do both left and right endpoints? If I would have went from 2 to 4,
So it would just be the middle of they'd be the same.
they'd be the same. They'd be
mirror.
symmetric. Where one went over, the other one go equally over, and the other way, they would come out to be exactly the same. The fact that I went not around the center of this parabola, that's what makes the left and right different. Do you have to actually understand what I just said to do these problems? No. Just want to point it out. So this one should not take as long. We got most of the work done already. So now the last two rectangles are the only two that undershoot. And I don't know if you guys are, so I'm gonna do all the same shit I just did, except I'm not gonna have the first dude because that was the first height and I don't use that first height now. So I'm gonna start here. But now I have to add in the next triangle. I'm gonna do that. I'm gonna call it a triangle. So everybody just be worried about me and you're fine. I don't have to freaking put that in the calculator though, because I know it's gonna be 4. This is a freaking parabola, it's gonna go down the same that it went up, yes? Or plug it in. Does everybody see that? It's a slight shortcut. I've already done the work. I already know the heights for those. I just have to not use the first one and include the last one, because now I've shifted which endpoint gives me the height. So now I just have to add 3, so I have to add 1.5, so it should be 12.625.
Yeah.
Okay. Now, do you see how these are much closer to each other than the first one we did? Because we use 6 rectangles. My estimate should already be better, no matter which endpoint. But to make it even better, I still will go ahead and average those two, right? There's one. So 11.875. Yes. Okay. Now, and I'm really sorry. I probably shot ahead of where people are, but it's the same. It's the same stuff. It's the exact same process, right? We just have to be careful about which heights we're using. And then go ahead and try to do it in your calculator if you haven't done that yet. And then I'll talk about those symbols that are over there. Yes, sir. So if I do this in the calculator, I'll make sure I've got the function in there. Second, trace to get to calc. Everything up here is about graphing, so when I go to calc, it's calculating something about my graph. And I want to use the last dude. That symbol means the area under. So it graphs it. And then the nice thing I didn't say was, you tell it where you want to start. I want to start at 1, and I want to go to 4, and what's really cool visually is it shades that sucker in. It's kind of nice. So our estimate was 11,875, and the actual answer is 12. That's pretty good. It's pretty good. We only used 6 rectangles. So can you imagine if we used 12? 2 things. It would have been a better estimate, and we would have gone a little insane with 12. So I'm not going to make you, I normally don't make you do more than 6.
Yeah, we could have done it, but it would have been really annoying.
True. So I won't make you do it. Okay. It's just the same thing, just more of it, which is kind of silly. Okay. How do you guys feel about this? Is this the best thing we've done so far? Yes?
Like, is that how the calculator figures it out?
No. No.
Just like, we have like.
I know I said it the way I did because that's what I can connect it to for us right now. It does something different and we haven't learned it. So we'll get there. But right now that symbol does actually mean crank the rectangles up to infinity. But that's not what the calculator does. Otherwise we'd still be waiting. Wait, I'm only at 800 million rectangles. You do more.
Like, infinite, maybe it's a lot.
Oh yeah, it needs a lot, yeah. No. It doesn't do this process at all. It's gonna be the shortcut we learn eventually, but first we're gonna do a bunch of these. Ha. Okay. So I think what I wanna do, let me think. Let's do one more thing and then we'll take a break. I wanna kinda get us ready for the next section. Because the next section is where we're gonna take this process and we're gonna do it for an indeterminate number of rectangles. And then we're gonna let that go to infinity. So we're not gonna be concrete anymore in the next section, which you should have done this stuff. So this is getting us ready for what we have to do. So a couple things. Throwing a few things at you here. We already talked about this symbol a little bit last time. Yes. This just means sum of. So by itself, it's just a Greek letter. When I put stuff next to it, it becomes a mathematical operation. It becomes add up these. And I have to tell people, add up these for how long? Yes? So that's the little from 1 to n. So it's what we talked about last time. There are a few new things on here. For example, guys, if I add up 12 ones, what do I get? 12. If I add up 87 ones, what do I get? 87. So if I add up n ones, so I add 1 up n times, what do I get? N, just like you just told me, right? So if I ever see that, I know the answer is just n. What if it was the sum of 2 from 1 to n? 2n. Ooh, see guys. If I add 2 up, if I add 8 2's up, I get twice 8. I get 16, correct? If I add 8 2's up, I'll get 16, which is twice 8. Okay. So we would. Now, before I talk about this next dude, I want to tell you a story. A little story. You guys all know what an urban legend is? We're going to talk about a math urban legend, so it doesn't really make for a good movie and stuff. The urban legend goes like this. Nobody dies in this stuff. Well, they're all dead because it's been a long time. Supposedly, there was this guy named Gauss, and when he was in grade school, little tiny Gauss. By the way, anybody know anything about magnetism? We measure magnetic field strength in Gauss. That's the units. So if you get a unit named after you, you friggin' made it. You're there. All right. Gauss, little tiny dude, right? In class, the teacher's like going crazy because everybody's just jumping on one, and the teacher says, "Everybody sit down. I want you to add up the numbers 1 through 100. If you say something before you're done, I'm going to kick you out, right?" And some of them are like, "That sounds good." No. So they start working. You guys with me? Everybody with me? Add up 1 through 100. Gauss, 7 seconds later, he's done. He comes up, "Here, teach, I'm done. I'm going to go do the shit I was doing a minute ago." All right? You guys with me? And the teacher's like, What? So he sits down, he's like, 1 plus 2 is 3. 3 plus 3 is 6. 6 plus, you guys, he does it. Just goes more, and then he says, "Holy shit, you got it right, little Gauss dude. Little overachiever." Right? You guys with me? Somebody kind of with me. Everybody? Does anyone know, has anyone heard, I don't know if you've ever heard that story before. It's a real story, by the way. Well, it's a real passed down by oral tradition story, sort of. We don't have any way to verify it. So the problem is, I want to add up 1 through 100. 999, Joe, that's good. But I want to do it in 7 seconds. Right? That seems kind of impossible. Has anyone ever seen where I'm going with this, do you think? Anybody? Some of you guys? Okay, so just sit there, don't stand there. If you just figured out where I'm going, you've never seen this before, then you can speak up. So if you do 1 plus 2 and then 3 plus 3, that's going to take way longer than 7 seconds, right? So here's what Gauss realized. Little Gauss dude said, "Wait a minute, 1 plus 100 is 101. What's 2 plus 99? What's 2 plus 99? 101. What's 3 plus 98? 101. You guys with me? How many pairs are going to make 101? 50. So we have 50 101s, correct? How'd you get 50?
Split 100.
We took 100 divided by 2, and then we did 1 plus 100 is the repeated sum, yes? 1 plus 100, 2 plus 99, we just kind of step in. What is 50 times 101?
5,055.
50-50,
Or 50.
which is insane. It's insane. 5 times 101 is 505, and then you put a 0 at the end, yes? 7 seconds. You with me? Number one, is anybody else freaked out if you didn't know this fact that the first 100 numbers added to be 50-50? Right? You say, what's the 1 through 100? Oh, I've got a 50-50 shot. What? What'd you say? So, you know, you can just kind of stumble on it. I know, it's a dumb joke, I don't care. Are you guys, I don't know, is anybody, now a few of you guys said you've seen this before. Okay, all right. Do you get the idea though? It's one of those stupid things, like somebody gives you one of those puzzles and you gotta make the one little piece kind of free. You ever seen those puzzles? And then when somebody shows you, you're like, God damn it. And you're over there going, I can't do that shit, I can't do that shit. Here, how do you do? Like this, oh, screw you. It's just this thing, this maneuver, you're like, I didn't even think about it. Same thing. You're like, oh shit, give me a break, little dude. Yes, it's very simple. So what does this look like in general? I can do this trick for any collection number, and to be honest, I could do this trick for any numbers where the distance between them is constant. You know, so that's 2, yeah, so I could do this. But here's the formula. What was the 100? Where did you get 100 from?
The total,
The total number. What was 1?
the starting number.
That was the first number. And in fact, we'll just say it's 1. We always want to start at 1 with these sums for the most part. So it's 1 is the first number. And the last number was n. And that is the sum. So the sum from 1 to n of I is n over 2 times n plus 1. And we just kind of like put those together. Do you guys see that? So if I want to go to 500, I would just do 500 divided by 2 times 501. And I can get the answer real easy. I don't have to add up 1 through 500. Thank you guys. Is that okay?
Your initial number was a different one, it would be, maybe the initial was 3.
Yeah, the general form of this says like A1 would be our first number plus AN would be our last number. Does that make sense? For us, our sums are almost going to start at 1. Yeah, almost always going to start at 1. So yeah, we'll use this more specific version. Yeah. And then this last piece we already talked about, right? If I added up 2n, the answer is, if I added up here, if I added up 2n times, the answer would be 2n. So if I have c times something, I could factor the c out. And by the way, what is this? I mean, I basically just gave it away. Isn't this an infinite sum? Isn't this c times 1 plus c times 2 plus c times 3 plus, can't I factor a c out? Isn't that just what that says? Factor the c out? That's it. That's all it is. So a constant can go in and come out. You guys with me? Do you see what I mean? Do you see how I slowed down when I said that? It was very important then. Next thing, what is the variable according to the summation symbol? What is the thing that it sees as a variable? What is changing for the summation? I is the only variable according to this guy. Is everybody with me? Sort of? Okay. So n is not a variable according to that guy. It could come out. It's a constant. Okay, maybe. So for example, if I do the sum I equals 1 to n of n, I can take an n out. Yes? And then what do I get? What's the sum of I equals 1 to n of 1? What do I get when I add 1 up n times? N. So the answer is n squared. Okay. All right, so let's try these out. This first one is very straightforward. We did examples like this last time. Remember, summation symbols are basically plug and chug and then add, because that's what the symbol means. Yes? So I is going to be, what are the values of I? 2?
1.
No. What are the values of I?
Up
2,
to 4.
3,
3
4.
and 4.
Yes? What does I always step by? 1. So unless it says otherwise. So I always goes by 1 with this symbol. Okay. So I want to add up all of these where I is 2, and then 3, and then 4. So it's really just plug a 2 in, plus, plug a 3 in, plus, plug a 4. So it's one step on top of plugging stuff into a function. Plug stuff into a function and then add them all up. So what do I plug in first? 2 plus plug in a 3 plus plug in a 4. And then I figure it out. So this is I equals 2, I equals 3, I equals 4.
Oh,
And just to go back to what I said earlier, most of the time we'll start at 1, not all the time. Now you just gotta do that, right? What's 10 minus 4? That's 6, that's crazy. What's 15 minus 8?
7.
7. And what's 20 minus
4.
16? 4. So then I get
17.
17. Oh, that's fine. You'll be fine.
I'll be okay.
So look at number 2. What's kind of, well, the only difference really immediately is I put the function definition out here instead of inside. Like on the first one, I could have said f of x is equal to 5x minus 2 to the x, right? And then f of I is inside. What can I do with that n? I can take it out. So I'm going to take it out, and then if I wanted to, just to make this look more like what I'm used to, is what's f of I? Here's f of x. What's f of I? Now this piece looks just like the first one we did, yes? F of x, they told me here, that's f of I. So I can put an I in, and that's what's actually inside. The n is a constant, because what's the only thing this thinks is a variable? Is I, so the n can come out. Every constant can be factored out. What's the only thing you can't take out of the summation system? Something related to I. It has an I in it, you can't take it out. Okay, maybe, probably. And now you just plug shit in. Right? Yeah. Thank you. Just to make sure we know the minus 3 i's in there. Like that. So then we get n times 1 minus 3 plus 4 minus 6. Is everybody with me? Just plug a 2 in, now plug a 3 in. 9 minus 9. So then you get negative 2 plus negative 2 plus 0, negative 4n. Whee! Okay. Now these two come at you out of nowhere, I think, but that's too bad. Because again, what are we going to do? What are we going to do in 5.2? We're going to do what I said is going to make our estimate become perfect. It's not going to be an estimate anymore. It's going to be the answer. And how do we do that? We take the number of rectangles we want to go to infinity. So if n is the number of rectangles, we are eventually going to let n go to infinity to crank the resolution up to infinite. Yes? That would be an insane TV. Your minds would melt. More resolution than reality. How do I do this limit? How do I do this limit? How did you do that so fast? How old up?
So you just look at the highest coefficient?
Yeah, so if you multiply the top out, what's the degrees on the top and bottom? They're the same. So then what's this limit going to be? 1/2, the ratio, the coefficients, yes, you guys remember? That's a remarkably good thing to know. Comes in a lot of times. And I'm telling you right now, this is gonna happen a lot. Now somehow, this connects to this. Let's see if you guys see how. Let me ask you this, you ready? Okay, this is huge, because this is gonna come up. What does the summation symbol see as the variable? I. What does the limit see as a variable? N. What can't come out of the sum symbol? Anything that has an I in it, yes? What can't go out of the limit? Anything that has an N in it. So let me try this again. This guy sees the variable as I, because literally that's what's changing for it, right? Therefore, I can't take an I out. I can only take out a constant. This is a constant according to him. That can come out. How far can it go out? It can't go here, because this guy sees N as the variable. Do you guys see that?
So that's good.
This is going to happen in section 5.2. I say that very confidently. I think. So I'm going to take that out the way, because then I know what the sum of I is. We have the thing that we just did, the Gauss dude, yes? So if I could just get sum of I by itself, I know what the shit that is. Well, the N business is all a constant. You guys agree with me? Whatever N is, this is a constant. N could be 7, then that's a constant, yes. So it literally is a constant. So this is how I can do this. This can come out this far. Because he's cool with it and he ain't. He sees N as the variable. I can't take something with N in it all the way out because it's got to stop here. So I can take this part out of the sum. Does everybody see the one thing that happened there? There's one thing that happened. I took that, which is a constant according to him, I took him out. But then I had to stop here because he sees N as the variable, so I can't go past him. Okay. Now what's this? No, it's I, not 1. So go back, it's the Gauss dude, right? It's the Gauss dude.
N times N.
I know what the sum of I is. So I got the limit as n goes to infinity. 1 over n squared plus 1 times, replace this with,
N over 2.
and then do you see how that's the same problem? Does everybody see how those are the same problem? N times n plus 1 is n squared plus n. 2 times n squared plus 1 is 2n squared plus 2. Do you guys see how that's the same problem? So then this is 1/2. That's the kind of manipulation that's going to happen in section 5.2. You guys looking forward to that? Okay. Thankfully, it just is there for a little bit. I really hope that you get it. How much have we done with it so far? One problem. Okay. So let's give it a chance. Let's go ahead and take a break. Why don't you come back at 10 after? Okay.
I don't want to do no more math, Jeff.
Too bad. Damn it. This is college. You can leave anytime you want. Okay. It's the opposite. Well, it's better than Hotel California. Check in and you can go. Okay. So what we're about to do is, oh, that's right. Before I do back to this. Yes. So just, you don't have to redo anything or anything, I just wanna kind of point out this notation over here. If I, what was this one? Yeah. If I call like this guy x1, and then the next thing I've got to use is x2, and then the next thing is x3, are you guys kind of with me? So I'm trying to do this, I'm trying to develop a general way to tell somebody else what to do. So the first thing we did was we figured out the specific inputs we need to use to get the heights, yes? We got the width, and then I could use that to figure out what the first rectangle starts at, what the next rectangle starts at. Are you guys with me? So that was the putting down the widths of each rectangle using the width, getting what their endpoints are. Okay. That's the first step. If I had to use 858 rectangles, do you all agree that somewhere there would be an xi? Like every little, really want this to make sense. So in this one it was 1, 1.5, 2, 2.5. So x1 for us was 1, x2 was 1.5, x3 was 2, yes? Okay, in general, if I just know A to B, what's the first one? Let's call it x1. What's the next one? x2. All right, so give me a random one in the middle, xi, where I is just some number. Right? Are you guys at all with me? If I have to use 858 rectangles, one of them is going to be x73, yes? So give me the random one, xi, where I is whatever number. Stop for a minute. You guys with me? That's how I can denote this step of breaking the x-axis up into these little intervals. xi plus 1, xi plus 2. Okay. Then I take f of xi. That's this. What does this represent? When I plug it in, what do I actually get when I plug that number in? I get the what of the rectangle?
The length.
Height. And remind me what delta x was. The width. So what is f of xi times delta x? That's the area of the ith rectangle. It's the area. Don't do that. It's the area of the ith rectangle. Does that make sense when I say that? And then on this specific problem, how many rectangles did we want to use? So that's why I'm going to add up from 1 to 6 each height times width. So this is just capturing what the shit we did, but in more general speak. So in mathematics, we want to be able to give somebody else an algorithm. We want to say, here's what tells you what to do. So if I just give somebody this, it has everything in it. Figure out what this shit is, figure out what these are, plug them into this dude, multiply them, add them up. Everything is here, correct? Now, I'm not going to just do that to you and do this and say, figure out what the steps are, but you can see every step in here. Okay, maybe. That is the symbol that represents, and of course I use L for left endpoint. This is the left endpoint estimate using 6 rectangles. Okay, are we all okay? Are we all okay? Okay. Same thing for that guy. Okay. So, if I have... Oh, by the way, let me talk about one thing just by itself for a second. What about a function that did this? Can you guys copy that down on your paper? Doesn't have to be perfect. Just copy that idea down. Can you shade in the area between the function and the x-axis?
You'd have to do it separate.
Like this piece is easy, yes? This piece is also easy, yes? Can anyone tell me what's gonna be true about this piece? It's gonna have something that we have been told forever it cannot happen, but it can happen in mathematics. That area is gonna be negative because that area is not necessarily a physical area. Let me see if you guys are cool with this. If this is velocity and this is time, you with me? If this is velocity and this is time, what does it mean when I find the area? I would be doing height, which is velocity, times width, which is time. What's velocity times time? What's velocity times time? You have rate times time. Rate times time. 80 miles an hour for 2 hours. If I multiply those, I get how far I go. Yes? So rate times time is distance. T equals RT dirt. The dirt formula, yes? Alright, just stop for a minute. Whatever the unit is on the y-axis, and whatever the unit is on the x-axis, when I get an area, I am literally multiplying those together. So if this is miles per hour, and this is hours, when I get the area, I actually get the distance I've gone. Yes? Okay, or better for this example, because this is negative distance, which just means I'm going the opposite direction. Something might make a little more sense. What if this was profit per day, and this was days? What's profit per day times days? Profit, right? So this, of course, that would be the total profit over how many days, correct? What would this mean? We lost money. So is that not a physical idea? Isn't that a physical idea? We lost money. That is a physical idea that we have lived in this physical world all the damn time. You guys with me? I need you with me. So when I say, I'm going to say this a few times, that area is negative. You all know I'm not talking about the area of the foundation of a house. Because what the shit did I make that out of if that's negative? I'm talking about area meaning the mathematical concept, where that could mean profit and that could be negative, can't it? It could mean temperature. And on our scale, that could be negative. Yes? Maybe. It could be heat lost or gained, and if it's lost, it's negative. Okay, maybe. Is everybody cool with that? That area, we understand it's not really physical area. It's the area which is the interpretation of this unit times that unit. Because that's what area is, length times width. But if I do this unit times that unit, it could come out negative. Alright, so I am going to say negative area sometimes. Some of my colleagues don't like that I do that, and I seem to not give a shit. Because that's what it is. Okay. Oh good, so I got both of those ideas. Okay. So, let me start clean here. They give us, so just accepting it can be negative sometimes. I'll give us one that isn't at the moment so we can just focus on this idea. Why did I do that? It doesn't matter, John. Okay. So, A to B. And I want to get this area, but I want to use n rectangles. What will my width be? In this case, it's kind of silly. B minus A divided by n. So it's really just the formula, right? Okay. Okay. Now, to remind myself of one thing, which way did I want to go? Oh, here. No. Did I want to go? I had chosen one way to go. Shit, I think I left them somewhere. All right, I'll go get them. It must be on my printer. I now want to figure out the xi. the general location of a rectangle. I want to be able to write in general the area of a rectangle. They're all found the same way, aren't they? They're found by plugging xi into the function and then multiplying by the width. They're all found the exact same way. So, xi, let me see if you guys are cool with this. If I start at A, how do I get to the ith thing? How many steps do I have to take?
Infinite.
So like, let's say I'm using right endpoints. x1 would be one step away, yes? So for example, x1 would be start at A and take one step. Because what's delta x? It's how big each step is. So how would I get to x2? I'd start at A and I'd take 2 steps. Give me 2 steps. So how do I get to xi? How do I get to the ith rectangle? How many steps do I take?
But A plus 1.
Good, I steps. To get the first rectangle is 1 step, to get to the second is 2 steps, to get to the ith rectangle it's I steps. I is just a number I don't know yet. So somebody's like, I'm at the 7th rectangle. Oh, it takes 7 steps. What about you? I don't know. You take that many, I don't know steps. I'll call it I. Stop for a minute. Real quick. Let me give you a concrete thing about what I'm talking about. If I can find my paper, it'll be alright. Oh, this is fine. For this one, real quick, for this one. How do I get, so this is the first rectangle was here, the second rectangle was here, third rectangle was here. How did I get to the third rectangle? Don't I start at 1 and I go 1, 2, start here, 1, I could do it, Jeff, 2, and then 3. That's the part I couldn't remember. So if I say this is like the first, and then 2 more steps gets me to the third rectangle. So if I start at A, and I go I steps, I'll get to the ith interval on my x-axis. Okay. So we had to, when I did the 1, 1.5, 2, 2.5, how did we determine those values? We started at A, which was 1, and then we just kept adding delta x. We just kept adding our width. That's all this is saying. If you start at at A, and you add so many widths, you'll get to the ith subinterval. Okay. So this is the width of a rectangle. Have I written the height of the rectangle yet? No. How do I get the height again? Just let go of what we're doing right now. How did we get the height? Yeah, we had to plug something into our function. Right? We had to plug our x1, x2, x3. We had to plug that into our function, yes? So if I do f of xi, this is the non-concrete version. So let me give you a concrete. Let me give you a little concrete, a little side note. If A is 1 like it was on this problem, if A is 1 like it was on this problem, yes? And delta x is 0.5 like it was on that problem, how do I get to, so I start at 1, if I want to get to the third thing after 1, if I want to get to this one, first, second, third, if I want to get to this one, I'm going to do 1 plus 2 steps. So I'm gonna do 1 plus 2 of these. To get to the start of to get to the second rectangle, I should say, not triangle, rectangle. So if I start at 1 and I take 2 steps and every step is half big, that's how we got to 2. And then we took that and we shoved it into the function to see what the height was there. So I can see how tall that rectangle was. Okay. Oh, okay. So now I've got the width of each rectangle. I've got the height of each rectangle. Now I can do the part where we can make the area. So what's the area of each rectangle? It's gonna be this times this. And then, what do I do once I get all the areas? What did we do once we got all the areas? We added them up. But of course, how many rectangles did I say we're using? N. This is effectively what we did on the problem when n was 6. We did all these steps, n was 6. But what are we gonna do now to ramp this resolution up? We're gonna let n go to infinity. This is the formula for the exact area. And I thought for sure I had brought those. Apparently not. Oh wait, is it on the other side of that? No. Oh yeah, that's that one. Alright, I think I'm back in my office. So, let me run back to my office. I've got this on this little worksheet. We're gonna do an example of this. So I'll be right back. Alright, let's take a look here. So I'm trying to find the exact area. So we're gonna let the number of rectangles go to infinity. This is the form we just kind of developed. I sort of did halfway between both, but it's okay. Here's that step I talked about. To get the ith step, I take a plus I delta x to get there. Then I plug that in. So what gets everything started? The most important step in this whole thing is delta x. It gets everything started. Figure out what delta x is. Then you can figure out the expression for the ith interval piece, the ith input. Then you take that and you input it. Now listen, we'll do an example. This whole thing is not concrete because we're letting the number of rectangles go to infinity. We have no idea at any point, any specific number of rectangles. Every step is the exact same when I did 6 rectangles. It just is gonna look worse because we're gonna have n running all over the place. So here's a fleshed out example here with a very simple function. Right, so I got my delta x, 5 minus 2 divided by n. Get what xi is, plug that into the function. That's the height. So this is the heights. This is the widths. So if I just take the heights times the widths and add them up, I'll get the area. Right? Heights times widths is the area of a rectangle. Add them all up, I get the total area. And now I just have to simplify. Okay. So I'm not gonna, let's do an example, because just stepping through an example that's already done, you don't see it happening, so it's easy to get lost in the middle of everything. So let's try a specific one out. Interest of time, I'm gonna skip the first step. First step is just doing what we did earlier. 4 rectangles, blah, 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 yes? Let's try the second step. Not sure what happened here, this poor little dude. But you know, the printer just is asking for a break, I think. It's telling me slim will be okay. So can somebody tell me, number 2, we're trying to find the area under that thing up graphed above from 0 to 3. It's a little evil that I chose one where I start at 0 because 0 makes everything nice. I'm gonna add it to something, it's okay. Just wanna point that out. It's not always gonna be 0. Can somebody tell me how to get delta x? How do I get the width?
3 minus 0, right?
Yes. It's the same thing as always. B minus A. How far total do I have to go? Divided by how many rectangles I'm using, and I'm gonna use an infinite number. Eventually, I'm gonna use n rectangles for now, and then later I'm gonna let it go to infinity. So when you're doing this kind of problem where I want us to use an infinite sum, your width is always gonna be a number divided by n. Always. So if the number of rectangles was 6, this would be a half, like it was on the other problem we did. The very next thing we did, once we knew what the width was, the very next thing we did was we set up the subintervals on our x-axis, right? We figured out what x1, x2, x3 was. We figured out those little x values, yes? So that's the very next thing we do here. We figure out what xi is. And xi is always start at the beginning. That's crazy, Jeff. And go this many steps. And just reminding you, I mean, this doesn't always have to be 0. So your xi is pretty much always going to be a number plus something I over n. You guys see that? It's pretty much always going to be that. Since that was 0, it just comes down to just 3i over n. That kicks ass. Okay. What's the next thing we did? So this is exactly all the same steps we did before. We figured out what the width was. We used the width to figure out where our rectangles are going to be on the x-axis. Very next thing we did was determine the heights of each. Yes? And again, how did we determine the heights for each rectangle? Plug in the x piece, right? So I'm going to plug in xi. So now I need f of xi to get the height. So that's going to be f of 3i over n. So I'm just going to take this and I'm going to shove it into this. 4 plus 3 times 3i over n minus 3i over n squared. Okay. And then simplify this a little bit. What does that represent again? My heights. So if I take, okay, now I just got to fill stuff in. The limit is n goes to infinity. The sum, I equals 1 to n. F of xi is my heights. Delta x is my width. So I'm adding a bunch of areas of rectangles, yes? I'm adding areas of rectangles. And the last thing I worry about doing is letting the number of rectangles go to infinity. So this guy here you can basically forget about until you're done simplifying the sum. Let me stop for a minute. This is a process that it's easy to lose touch with what it represents. That's why I keep trying to remind you, this represents the width, this represents the height, this represents the area when you multiply those together. How are we doing? Yes?
If I is the first steps we take, why is it only one and under the sigma?
Why is it what now?
Why is it only one under the sigma?
No, it isn't only one. It goes from 1 to n. Yeah, okay. So you're good. The bottom part just tells you where the variable starts, where I starts, and the top tells you where it goes to. Yeah. Okay. So now it's some algebra for a moment. Can you distribute this in?
You wouldn't factor?
Say it.
You wouldn't factor the 3?
Move it in front of the,
Like if
Oh yeah, you could take the 3 out, sure. You want to do that? You can do that.
we're just one.
Yeah, if you notice, you could take the 3 out. Does everybody notice you could take the 3 out? I mean, now you do, but maybe not before. Yeah, okay. So let's do it this way. You'll see, it doesn't matter. It's not going to really affect things too much. Yeah. But you could, totally. So 3 over n times 4, you're not going to believe this. It's 12 over n. What's 3 over n times 9i over n?
27 I over x squared.
And then 3 over n times 9i squared over n squared.
27 I squared over n cubed.
Oh boy, the king of not enough space is back. There, okay. We write that over again. Over n plus 27i over n squared minus 27i squared over n cubed. Is everybody excited? Somebody did this. Yes, I'm very excited. Now, let me ask you this. Quick little side note. If I had to add a bunch of, here, if I had to add these numbers, if you wanted to, couldn't you add up all the negatives first? Where are my fellow old people? We, back in the day when we balanced our checkbook. You could take all the positives, all the negatives, add them all up separate, and then add those together at the end, yes? So what I'm saying is, I'm adding up things. I can add just these, plus add this, so I can do this. It looks like the summation symbol distributed. It did not. But it looks like it did, so you can look at it that way if you want to. Does that make sense? If I have to add up A plus B 7 times, can't you add up A 7 times and add up B 7 times and then add those together? Right? That's all that thing says. I have to add up a bunch of this plus this. Okay, I can add up all these, I can add up all those, and then add that to all these, and then subtract what I get if I add up all those. That's the, so I add up all the debt and add up all the debits and the credits, and then add those together at the end. Okay. I'm really bad at business. And you guys all know, you can add whatever order you want to. You guys agree with me? If all you're doing is adding, you can add whatever order. What does this mean? Add. And then inside here I'm adding, and minus is adding the opposite, yes? So the only operation, this whole thing is adding. So I can add whatever the hell order I want to. They're all on the same level. So therefore, I can kind of combine I can add just these, and then I can add just these, and then I can add just these, and then I can add all that together at the end. I get the same answer. So if again, a concrete example. If I had to add up A plus B 7 times, couldn't I add up all the A's and then also add up all the B's? Then I'll get 7 A's and 7 B's, which is what here I would get 7 A plus B's, which is 7 A's plus 7 B's, yes? That's all I'm doing. That's it, that's all I'm doing. So I can add up each individual piece. Now what does that do for me? I wish I knew. Oh yeah. That is one little thing I have to point out. Did I put that on there? Probably. Yeah, here. Yeah, I'll come back to that. Okay, we'll come back. So this one, what can I take out of this sum? What can come out of it? Just that first one right there. What can come out of this sum? 12 over n. The whole thing can come out, yes? Because what's the only thing this thinks is a variable? I. So I can take 12 over n, and I'm left with 1. And we know what that is. What do I get when I add 1 up n times? N. So this is n, which kicks ass. What can I do with this one? What's the only thing that I cannot take out of this one? No, the I. I can take 27 out, right? So I can take 27. Do you see, Paula? It didn't really matter if you take it out first or later. Yeah. Since I'm doing each one individually, it's actually better just to put it in there, yeah. Okay, really quickly. Do you guys see this is the same thing? All they did was take the 27 over n squared and take it out, yes. Why am I allowed to do that? Because those are constants according to the sum. Those are constants. If I have a long string of things I'm adding and every single element has a b in it, I can freaking take a b out. So I have a long string of things I'm adding and every single element has 27 over n squared. Now real quick, why does it not make sense to say every element has an I in it so that I can take it out? Is I a number?
No, that's a very.
What's happening to I? It's changing. I is a variable, so I can't take an I out because I don't know what I could be 1, I could be 2, I could be 847 billion. Well, what's 27? 27. What's n squared?
Constant.
N squared. It's what it is. It's not changing, so I can take it out. It is in every term. Here, the first term has a 1, the second term has a 2, the third term has a 3. That's not the same thing in every one. That's why I cannot take an I out. Yes? Because it's not the same in every expression then. It's changing. And then what is this? Yeah, that's Gauss dude. I'm sorry, maybe I'll stop yelling. Okay. I'll get past. Now what can come out of this crazy dude here?
27 over n cubed.
Now this is the one we haven't talked about, and this is the one that I have a proof for. I can put it up in Canvas because I don't know if you guys want to sit through it, but on the paper I gave you, the one with the, look, it's got a color on it, so leave me alone. We got the Gauss dude here, yes? Then we have the one that is definitely not obvious. That is not obvious, do you agree? Okay. So do you see how that's showing up here? So let's do this. Let's finish this up. I'll talk a little bit about this maybe next time. Let's finish this up. I can replace this with this. It's all right. I might finally have it memorized. Okay, so remember what happened over here? The limit of 12 is 12. Now, can anyone help me with the limit as n goes to infinity of this? What would the degree of the top be? 2, yeah, second degree. And what's the degree of the bottom?
2.
So what's the limit as n goes to infinity?
27 over 2.
27 over 2. Because the degrees are the same, the limit is the ratio of the leading coefficients. Then the limit of this one, same idea. Be really careful though, be very, very careful. This degree is 2, yes? Sorry, this degree is 3. But the leading coefficient inside would be
It's
2,
2.
yes? Okay, so let's keep that in mind. That degree is 3, that degree is 3.
So 2
The limit is the ratio of the leading coefficients,
1/3.
which is 54 over 6. 54 divided by 6 is
9.
9.
Minus
12 minus 9 is 2, plus 27 halves is 31 halves. Yes? 12 minus 9 is 2. Did I really just say that? 12 minus 9 is 3, plus 27 halves is 33 halves, which is 16.5. So that is the exact area under this. Yeah. I want to do one more thing, but I think I'll leave this till next time to talk about the specifics. But one more thing. Let me see if I can sneak this in. Can somebody do the antiderivative for this?
X 1/4 x.
Good. And then, yeah, x would become x squared, which is, will be 3/2 x squared. Is that cool?
Yeah, it's
1/3.
The gas plus e, right? So watch this. What's big ass f of 3 minus big ass f of 0? Let's see. Big ass f of 3 would be 12 plus 27/2 minus 27/3 minus 9 plus c. Is everybody kind of with me? I'm just doing what the guy who did this told me to do. Just doing what I told myself to do. Evaluate big ass f of 3 minus big ass f of 0 is just c, yes? Which is, does that look familiar?
Mm-hmm.
So it comes out to be 16.5. Interesting. There seems to possibly be a connection between finding the area under a curve and that function's antiderivative.
Yeah, I think it's a lot easier.
That will lead to our short. We still have to prove it because this could just be a coincidence. It could just be a coincidence it came out to the same thing. Spoiler alert, it isn't. But right now, as far as everything we've done, that could just be a coincidence. So we still have to prove that finding the area under a curve is related to just getting its antiderivative. So, would you rather do, I know the answer. Would you rather do this every single time?
No,
Or would you rather just take the antiderivative and plug shit in?
yes.
Yes. So this is the equivalent of like limit definition derivative, but I think you all agree that it's worse. Yes? And then this, we have to prove it before you can use it. So don't be using it before you officially know it in the homework. This is everybody's kind of trouble is sometimes you don't get the homework immediately and then you start using stuff you don't know yet.
How are we supposed to know?
When you get to the section where you're taught it, yes. So, all right, that's plenty. All right. Thanks for putting up with me. I'll see y'all. What is today? Wednesday? I'll see y'all next week. Have a good weekend. Get out and touch grass and do all kinds of stuff. You don't like touching grass? Okay. Don't. Stay inside. Play some Outer Worlds. All right. Do something in the middle.
Stapler wrench?
Yeah. Oh, there it is.